Well, like Roger, I've been working on the climate issue since longer than I can remember. And I've also been very heavily involved over the past decade in the work of the Intergovernmental Panel on Climate Change. And I wanted to open the sort of science talks of this meeting. There's a lot of very interesting science talks to come about the details of how climate change will affect delta regions of the world. But I've been asked just to give you the big picture of the latest evidence from the IPCC and summarize some of the key messages as I see them coming out of the latest IPCC cycle. Most of what I'll be saying, you'll tell from the IPCC background of the slides, is material from the reports. But since I'm here, I can't resist, particularly I don't often get a minister in front of me, finishing up with a couple of slides of my own personal views, and it will be clear where it's my personal views rather than the IPCC when we get on to particularly the mitigation question that Roger mentioned at the end of the minister's talk. First of all, crucially, the IPCC reiterated that it's extremely likely that human influence is the dominant cause of the warming we've seen over the past 50 years. And this slide just shows you the warming pattern observed over the past century. And as you can see, even though globally we've seen less than a degree of warming on average in certain regions, in the centers of continents, and also very importantly in tropical regions, where the impact of warming is substantially greater because these regions don't experience so much interannual and interdecadal variability as we see in mid-latitudes, we see warming even higher than 1 degree already. So this is the background, the observed changes we're already seeing, and the IPCC also concluded that this warming is extremely likely primarily due, the dominant cause was the human influence on climate, for the simple reason that you can't explain what we've seen without human influence on climate. If you just compare the red lines on this figure, which are many, many simulations of climate models performed, including human influence, they match the observations very well, both over the land and over the oceans. And then you compare that with the blue lines, which show what happens if you leave out human influence. You can see you can't explain what's happened without human influence playing a dominant role in the warming that's been seen over the past 50 years. There's been much discussion over the past few years about the so-called pause in the warming that has been observed. You'll notice on this figure, this pause in the warming is very much an ocean affair. It actually mostly originates from the tropical Pacific with some role of the North Atlantic. Land temperatures have continued to warm as predicted. We expect more variability in the oceans, and there's nothing about this so-called warming pause that really changes the big picture of what we expect for the future. And I'll come back to that point about how complete the agreement is on the big picture for the future later in the talk. Importantly, the IPCC for the first time reported that we are now observing impacts of climate change on natural and human systems in all continents of the world. So here in Europe, we're seeing impacts on marine systems, a lot of that arising from ocean, some of that potentially arising from ocean acidification. We're seeing physical impacts on glaciers in the Alps. We're seeing impacts on human health and welfare. And we're seeing impacts on wildfires. So these are observed impacts which are already emerging in climate change. And of course, as the minister stressed and the mayor stressed, in delta regions of the world, we should expect some of the most highest sensitivity to climate change. These are particularly vulnerable regions, partly, of course, because so many people are moving to the massive delta cities of the world, but also because these are the regions that are vulnerable to sea level rise. Let me just summarize here the sort of image of sea level rise, again coming out of the IPCC latest assessment. This is the best estimate sea level rise. And this is not the highest estimate. This is just the average of the estimates of sea level rise on the left from all factors by the end of this century. And as you can see, the sort of overall color there is this orange color, meaning sort of slightly over 0.5 meter of sea level rise over most of the regions of the world. But it's important to remember there are regions where local sea levels will rise substantially more than that global average. It's easy to hear about a global average figure and think, well, that's going to apply everywhere. But there are regions, the US eastern seaboard in particular, which are predicted with confidence to experience substantially greater sea level rise than the global average. And that would also apply, of course, if we actually see a higher than expected sea level rise. There are various factors contributing to this, and I've just shown you these on the right because I do think it is interesting to remember the different things that contribute to regional sea level. The simplest one, of course, is at the top panel on the right, is the effect of thermal expansion. So here we have the pattern of warming just resulting from water. When you heat it up, it gets a bit bigger. So that's the pattern of warming you see. But we also see changes going on over the coming century. This is the entirely natural impact of the rising of some continents, falling of others, as they rebound from the last ice age. Then we have the impact of melting glaciers, which interestingly, and melting ice sheets, let's just focus on this one here. Notice that melting ice sheets, of course, causes sea levels to rise in most of the world, because, of course, the water from the ice sheets has to go somewhere, but we actually get a local reduction in relative sea level around the ice sheet itself, because that enormous mass of ice, the gravitational attraction of that mass of ice, has been pulling the ocean towards it. And as it melts, the ocean is allowed to slide away, and we actually see a local reduction in sea level. I find it personally quite extraordinary that human influence on climate can actually be affecting the gravitational field of our planet. It really puts the enormity of what's going on into perspective when you realize that's actually what's going on here. We're seeing the gravity field of the very planet we live on changing as a result of the warming induced by human activity. If we translate this into practical terms, this is a figure from the IPCC Working Group 2 report looking at the impact of these sea level increases on the required increase in flood defenses by the end of the century in order to maintain the same risk of exceedance. And of course, in many delta cities of the world, it's already been decided that we're not happy with current levels of risk, never mind the likely increased levels of risk we might see under climate change. So again, notice there's a lot of variety around the world. Off the US eastern seaboard, defenses would have to be raised by almost a meter in order just to maintain today's level of risk of inundation or defenses being overwhelmed. In Europe, it's perhaps half a meter. And there are many specialists in coastal defenses in this room, so I needn't emphasize to you the enormous cost of enhancing sea defenses by half a meter. That's one point to draw from this. The other point, of course, to notice is that these increases, which are primarily there to defend against storm surge events, these are the situations in which coastal defenses are likely to be overwhelmed, these increases are relatively small compared to the size of storm surges in these regions of the world. And this actually brings me to my most important point, that certainly during our lifetimes, climate change will manifest itself not through things that we simply could not have seen or would not have seen without climate change, but through changing the risk, making bad weather events worse. In fact, there was a good quote I heard recently on US radio. He was a firefighter in California, I think it was, and they were talking about the wildfires going on, raging through California, and they'd mentioned the role of climate change in this, and the firefighter put it very, very well. He said, yeah, you know, we've had fires, but climate change, it makes a bad day worse. And I thought that was a very nice way of putting it, that we're not, you know, we've always had harmful weather events. We will continue to have harmful weather events. But what we're seeing is the impact of climate change increasing the impact of those events and making a bad day worse. So this is the way, increasingly, we have to understand human influence on climate. we're not seeing, this is the image I like to use, the image I think everybody should get used to, the idea that climate change is loading the weather dice towards some kind of weather events and away from others. Importantly, if I threw all these dice for you, you'd say, well, it just looks like a bunch of dice. But if you look more carefully, you'll realize there is something wrong here. There's too many sixes. And the point is that each of those sixes, you couldn't say, if I just grabbed one of those dice and said, did climate change cause that six? Well, we might have had the six anyway. And whenever an extreme weather event happens, there's always somebody's going to pop up and say, well, I saw a record in 1563 that we had a flood like this one. The key point is not that climate change is making these events inevitable, or that we could not have seen these events without climate change, but that the risks are changing. And as a result, you're going to have to get used to complicated diagrams like this one. This, for the engineers in the audience, shows a plot of flood risk going up as you get to longer and longer return times, so lower probability of floods occurring each year. The blue line is the way we think things are now, and the green lines on the left are the way we think they might have been if we hadn't raised greenhouse gas levels, if we hadn't caused global warming. And so the crucial point here is that, broadly speaking, most of the green bubbles are down below the blue one, which means for this kind of flood, a fluvial flood in the autumn in the UK, the human influence on climate has increased the risk of that kind of flood. It's important for me to show you the right-hand panel as well, which also featured in the IPCC report, which emphasized that for other kinds of floods, the impact of human influence on climate has actually been to make them less likely. This is a snowmelt flood in the north of the UK. The last time we had really serious floods like this was in 1947 in the UK. And it's a different sequence of events. We don't get that sort of accumulation of snow in the UK anymore. So this kind of flood has become less likely. So it's not, whenever an extreme weather event happens, we often hear it being blamed on climate change, but it's important to recognize there is a science to be done here. Some extreme weather events are being made more likely, some less likely, and we need to understand. I think the main priority for my discipline over the next decade is going to be to understand which is which in order to tell people which are the weather events that are becoming more likely and which less. So here's my sort of conclusions on the observed and projected changes I've talked about so far. First of all, human influence on climate is clear. That's the main message coming out of the latest IPCC report. The recent pause in ocean surface warming, it's only the surface warming, down at ocean depths the warming has continued, don't change this big picture. We are seeing impacts on all continents and in many sectors, and in my personal view, the most important impacts over the coming decades will arise from changing risks of extreme weather events. This business, this science of understanding and attributing changes in risk is relatively new, but when we look at the global level, the science is clear and the overall trajectory is clear and the main drivers are also clear. And as I said, I warned you, since I have the podium, so I just want to say a little bit about these drivers and what they mean for the future, and also what they mean for what's being talked about, or what was being talked about in New York this week. The first important point for mitigation made by the Intergovernmental Panel on Climate Change in its latest assessment is this figure, which I think deserves to be on everybody's office wall. I hope it's on your wall, Minister. It shows the impact of the accumulation of carbon dioxide in the atmosphere and its impact on global temperatures. And it's a very simple message. In the horizontal, we plot the total amount of carbon we dump in the atmosphere since the beginning of the Industrial Revolution. And in the vertical axis, we show the temperature we get. And the key message of this figure is very simple. The more carbon you dump, the warmer it gets. And you might think, well, that's completely obvious. But a lot of the discussions are not about the accumulation of carbon in the atmosphere, but they're about the rate of how fast we dump carbon in the atmosphere. So we heard that China's announced they will peak emissions. Well, if China peaks emissions, it's just that China has made an announcement this week, so I'm using that as an example. I'm not picking on China here, but so if we collectively peak emissions but then we only bring them down very, very slowly, so they remain high. So emissions go up and then they come down very high. Think about what's going to happen on this graph. We'll carry on emitting. It'll carry on accumulating. We'll keep moving up the graph. So peaking emissions is not enough. If we want temperatures to stop rising, we need to bring carbon dioxide emissions to zero. That's why we need net zero before the century is out if we're going to stop climate change. And that has very profound implications, because the kind of technologies that are needed to get us to net zero are not necessarily the technologies that are going to allow us to peak emissions in the short term. That's where we are now, moving up this graph. Let's hope we stay down in the bottom half of it, but there's no guarantee we will do so. There's very high level of agreement on this overall response. There's quite a lot of uncertainty in it, but these are just lots of studies surveyed by the IPCC showing the amount of warming we get for a given injection of carbon into the atmosphere. And I just thought that since I'm speaking in Holland here, I thought I'd highlight one, it wasn't exactly a scientific study, but it was a report from a climate skeptic organization, the Global Warming Policy Foundation. It's a very strident critic of the IPCC. They produced a report, and they made an assessment of this quantity, the warming you get at the time of CO2 doubling in the atmosphere. It's a standard measure. And I think what was really striking earlier this year is that they end up with exactly the same numbers as everybody else. So the agreement on the global response is now universal. There's a lot of uncertainty. We can argue about whether we're here or there, but we all agree that that's basically where we're going. Back to this figure about cumulative emissions. The crucial reason why this figure is so important is if we compare the amount of carbon we can afford to dump in the atmosphere before we exceed 2 degrees with the amount of fossil carbon that's down there. That's what we've emitted so far, just over it's around 500 billion tons of fossil carbon. If we include estimates of conventional reserves, and engineers are very good at keeping these, increasing these as they find more and more sources of fossil carbon. That takes us up to 1.5 trillion tons. And if we include all the unconventional reserves, the fracking, the natural gas fracking, all the new forms of fossil carbon people are coming up with, it takes us up to any number we might care to contemplate. And crucially, therefore, if we are to meet the 2-degree goal, all of that has to be, if it's used at all, has to be either sequestered or recaptured, sucked back out of the atmosphere if we're going to meet the 2-degree goal. And this is the third very important point on mitigation made in the IPCC that I want to draw your attention to. I really want to draw your attention to this because it's really buried in the third report, which nobody reads. Everybody reads the first one and the second one, but nobody gets around to reading the one on what we're going to do about it. And this figure shows the cost of meeting the 2-degree goal if we allow all technologies, so do everything, or if we leave out various technologies. Interestingly, we can leave out nuclear, it just increases the cost by a few percent. We leave out solar, you might be surprised to know, it also just increases the cost by a few percent. But the big one, if we don't do carbon capture and storage, we more than double the cost of meeting the 2-degree goal. And I want to emphasize this, making my personal observation, the reason for this is that if we don't do carbon capture and storage, meeting the 2-degree goal means, in effect, telling the citizens of India of the 2080s not to use their coal. And I say we have no ethical justification for doing that. We have to develop the technology to allow them to use their coal without causing dangerous climate change. So this technology must be the priority now, and it's not being discussed in New York. It wasn't even on the agenda in New York. And the reason I want to talk about this is because I'm in Rotterdam, and just down the road, it wasn't in the mayor's, it wasn't in the video, but just down the road is the front line of the climate issue. You have the Maasvlakte power plant, which was built to bury CO2 into the North Sea to demonstrate this technology for Europe, and we're still waiting. And I think this is something Holland can seize, and Holland has an opportunity to take the world forward and develop the technology that we are going to need if we're going to meet the 2-degree goal. Thank you.
Thank you very much, Myles. I just want to take this opportunity, as he's ridden his hobby horse, to ride one of my own personal hobby horses, because he mentioned ocean acidification. I think this is a huge issue. If we didn't have climate change, people would be talking about ocean acidification. Humans are changing the chemistry of the oceans worldwide. The graph is linear in terms of the amount of CO2 that's taken up. We know exactly on current emissions trends what the pH of the ocean will be at the end of the century. And I went to Papua New Guinea earlier this year. I would urge you to see the film, 6 minutes. Google Papua Harabin, you'll find it. And it shows, with some natural CO2 vents, where scientists have been looking at what creatures can live at the pH which we will expect it to see by the end of the century. It's really shocking, the level of biodiversity, the numbers of creatures that are left at that level of pH. And I would urge you to see that. But Myles, I really also appreciate your emphasis on risk. I feel like we're far too much in the climate debate into a truth war about, oh, how much will the effect be in 50 years' time, or how much will the effect be of a doubling of CO2, and people arguing about the numbers. I think risk is a really useful prism, and we'll be talking about communication a bit more later on. But just before you go, I mean, I really gather a real sense of frustration from you about where the political discourse is and where the scientific discourse is, and the mismatch between them.
It is frustrating because, you know, I've been working like yourself, I've been working on this for so long, and in many ways, in certain key areas, we seem to be going backwards. One tends to emphasize where you think the problems are greatest. When I'm giving a lecture, I spend the most time on the areas where I think there's most confusion. So, we are making progress on renewables. I don't say that renewables are unimportant, but on carbon capture and storage, it's not me, it's not my hobby horse, the IPCC gives you the numbers. Without it, we can't meet the 2-degree goal, and globally, it's going backwards. And that's my concern. That's why I really wanted to put that into this, to make people in this room really think about that technology.
And why is it, do you think, that it's not catching on? Is it simply money, or is it that politicians don't understand the implications of it? What is it, do you think?
It's a very expensive technology which will take many decades to develop. It's not a quick fix. And we are going for the quick fixes. But quick fixes help you reduce the rate of the rate of emission of carbon dioxide into the atmosphere, but they don't solve the long-term problem. It's like, if you're in the desert and you've only got one can of water, I mean, yes, it's a good idea to drink it a bit slower, but in the end, unless you can find some more water, you're still doomed. So we're only focused on measures that help us drink the water a little bit slower. We're not thinking about the measures which are actually going to get us out of the problem we're in.
But let me push back at you a bit, because in Germany, for instance, there's a lot of resistance to carbon capture and storage. People don't want CO2 pumped under their homes. They're nervous about it. They think it might cause seismic activity, cause earthquakes. And there's a really big pushback against CCS in the major coal user in Europe.
Absolutely. And that's precisely the reason why we need to be developing this technology now, in order to demonstrate for the benefit of the citizens of the 2030s that it works and that it's safe. And we need to identify which reservoirs work and which reservoirs don't. It's ironic, of course, that under Berlin is Germany's natural gas reservoir. So people are perfectly happy to keep methane, highly explosive methane, under their cities because they're used to it. They've been doing it for decades. They know it's there. It's never blown up, so therefore it's not a problem. So when something's new, it takes time for it to be understood. And this is a technology that we will need. If our children look back at us in the 2030s, and will they thank us for the windmills? Perhaps. But what they will thank us for is a clear understanding of how CCS works and how they can implement it at scale.
Yeah, I mean, I think this is really ironic. I went to a BP plant in the middle of the Sahara about maybe 12, 15 years ago, a big natural gas plant. It would have been the biggest single point source emitter of CO2 in the world if they hadn't captured the CO2 waste from the gas and pumped it back into the field. So we're taking gas out of one end, the methane out of one end, pumping back CO2 into the other end. There was no seismic activity apparent, and that technology has been around. It's not as if it's new.
It's not new technology. It could be done. And it could be done here. It's just down the road. Go and look at the Maasvlakte power plant. Okay. It'll inspire you.
And the very good news is we still have a minister here to hear all that. So thank you, Myles.